first, it's very important with the mirrors that you know what types of mirrors form what types of images. And you saw that with the OpenStax right now. So just to remind you, we saw this, but just to summarize everything about mirrors and lenses. So with the mirrors, with the concave mirrors, we have three different types of situations. We have outside the focal point, at the focal point, and then inside the focal point. The image is real and inverted. This is like our big concave mirror when you're standing far back away from it. All right, remember I brought it in class and you all looked upside down when you're looking far away. This is no image. And this is a virtual, upright, bigger image. This is like when you get up really close to the mirror and your face looks huge, like it fills the whole mirror almost. So the images would look like this. I'll do them in green. The image here would look like that. Real images go on the same side as the object. So that has a positive image distance and a negative magnification. It's negative magnification because it's upside down. The value of the magnification could be bigger or smaller than 1, or even equal to 1. You don't really know. So I'm not going to say it's bigger or smaller. But it's inverted, so it's negative magnification. Here, no image at all, so Q is equal to infinity, and there is no magnification. And here, the image is over here. It's virtual, so that means negative Q. So if ever you have a virtual image, which you do on one of your OpenStax questions, it says it's a virtual image, right away you think, oh, Q is negative. And in that problem, it actually gave Q, but it just gave the value of it. And if you don't see that it's negative, then you're not going to get it right. It's upright. That means that it's positive magnification. And it's bigger. That means that magnification, the magnitude, is bigger than 1. So it's bigger than plus 1. Okay, we have one other situation with a convex mirror. This is convex. My focal point is back here, my object is back here, and my image is going to be virtual, upright, and smaller. This is like a security mirror, so my image will look like this. It's going to be smaller than the object. It's going to be negative Q, positive M because it's upright, and magnification less than 1. So the magnification is going to be between 0 and 1. Not equal to 1, less than 1. Not equal to 0, bigger than 0. And then with lenses, we saw very similar things. Listen, I can go through half those OpenStax questions, the calculations, and without even doing the numbers at all, like I can pick out the right answer just from knowing this. So I can look and say, well, if it's a virtual bigger image, the object has to be inside the focal point. And you can pick out the right answer without actually calculating anything at all. You can calculate and get the actual number, but you can pick out the right answer just by knowing these. Now, if my lenses are very, very similar, oh, by the way, these were concave mirrors, and concave mirrors have a positive focal point, focal length, and convex mirrors have a negative focal length. Over here, let's do it on the same side. I have convex lenses. They have three situations, and it's all the same. I'm not even going to write out the words again. I'll just draw the figures because they're all the same. I can have objects outside the focal point, at the focal point, or inside the focal point. And then I can also have or let's just draw the images now. The images are going to be over here. No image for the second one, and then a virtual bigger image over here. If you want to write the words, all these words that are over here, they can be translated over here. They're exactly the same. These do the same things to the light. I have a real inverted image. I have no image. I have a virtual upright bigger image. The only difference here is that virtual images now are on the same side as the object, whereas over here, virtual images are on the opposite side of the object. And real images are on the opposite side of the object, whereas real images on that side were on the same side of the object. So with lenses, this is the real space right here. With mirrors, the real space is on that side. That might sort of make sense to you, because if you want to project something with a lens, you put the projector screen opposite the object. But if you want to project something with a mirror, you can't put a projector screen back here, right? Because nothing's going to happen. You put the screen over here if you want to project something. Like when we burned the paper, that was the screen, right? We put it in front of the mirror because that's where the real image is. So it's exactly the same. The words are all exactly the same. Similarly, with our concave lens, notice that convex, concave, that's it, the language sort of trips you up a little bit. So with a concave lens, if I have my object over here, my image is going to be virtual, upright, and smaller. My image in green is going to be right there. And again, the words are all exactly the same. Also, I have minus focal length and a positive focal length here. Okay? Let's just look at an OpenStax question. Is that okay? Bree, do you mind if I pull up one of yours? It'll show the rest of the class and the rest of the world your answer. Is that okay? All right, let me. Okay, so what is the focal length of a makeup mirror that produces a magnification of 2 when a person's face is 8 centimeters away? So first of all, a makeup mirror, what kind of mirror is that? That is a convex or concave. It's a concave mirror, so I know that this mirror is a concave mirror. And I know that the magnification is 2. That means it's bigger. So let's think about my concave mirror. If my image is bigger, like that, then where is my object? This is my image. And by the way, I drew it as a virtual image because I know the concave mirror only produces a bigger image when it's virtual. And virtual images are always upright too. So with my makeup mirror, it wouldn't be very useful if I was upside down. So I know it has to be a virtual image, and I know that it's bigger too. So where is my object? Well, if I think back to those diagrams that I drew, my object for is going to be right here. My object's going to be inside the focal length. So my object then is going to be right here. So that's my object. So now I want to know what is the focal length. And I know that the person's face is 8 centimeters away. So I know that this distance is 8 centimeters away. I also know that the focal length is positive or negative for a concave mirror. Positive. It has a positive focal point. And so I can get rid of these right away. I can also get rid of this one because if the focal length was 5.3 centimeters, then that would put the focal point right here, which would mean I would have a real inverted image. So the answer has to be 16. Now I can go through and calculate that. I know that P is equal to 8, and well, it's actually a little more complicated. And then I say 2 is equal to negative Q divided by P. So Q then is negative 2 times P, which is negative 16. And then I have to find F. So it's not easy. You got to go through several steps. 1 over 8 plus 1 over negative 16 to the negative 1. But when you do that, you'll find that it's equal to positive 16. This is 2 over 16 minus 1 over 16 is 1 over 16 inverted, and it becomes 16. Look, I don't even have to do any of that because I can pick out the answer just by first getting rid of the negatives, because I know it can't be that, and then saying, oh, well, it's either in or outside the focal point. Well, then it has to be 16. Okay? Look for those kinds of questions. You'll be able to work through them, but you should be able to reason through them as well. Devlin?
Yeah, like number two, no section. I think it's just over. Like the first part I got, but the second part kind of stuff.
Okay, can I show them your number two? No, that's not it. This one?
Yeah.
Okay. I'm not saying that Bree's answers are right, okay? So, yeah, I think they probably are, but... And remember, I've already told you, I made a couple of changes to this one. I said that first, these should all be meters, and then I also said that A and B are just not, because they're replication, right? So, the first part is to find... let me look. So, how far away is the screen? Okay, yeah. So, how far away is the screen? That's asking what is Q. Right. I got my lens, I got my slide, that's my object, and I want to know where is my image. Where's that screen that I want to project my image onto? So, I want to find, well, let's just write down everything that I know. F is 100 millimeters, that's 0.1 meters. The slide, that's P, the object distance is 0.103 meters, and then I want to find Q. So that's 1 over F minus 1 over P, the inverse of that. I just solved my lens equation for Q. And that works out to be, well, it has to be 3.43 meters. It does work out to be 3.43 meters. Okay, and now I want to know how high is the projected image. Well, I'm given this value. The slide is 2.4 centimeters high. What is that? Well, I know my magnification is HI over HO, the height of the image over the height of the object. What is the 2.4? That's the object size, right? So that's equal to 2.4 HI. And my magnification, well, I don't know my magnification, but I can figure it out. It's minus Q divided by P. So that's going to be minus 3.43 divided by P, which is 0.103. I think this was like 33 or something. Is that right? Yeah, so it's minus 33. So in this magnifying glass or this slide projector, you take that little slide and you blow it up 33 times. And you also invert it. That's right. And so you get 33 times 2.4. But be careful, because this is negative. So when I multiply that, this is minus 33. When I multiply these two numbers, I get HI is a negative number. And what that means, if HI is negative, it means that my image is upside down. If my height of the image comes out negative, that means that it's inverted. Okay, these are excellent questions. They're good questions for the test. Okay? Y'all want to look at some of the old tests? Is that okay? I don't want to show all of Bree's answers. So far, she's doing well. All right. This is spring 15. So I would expect to see some questions like this, where I ask you, what type of lens or mirror is this? So if I have an object on one side and an inverted image on the same side as the object, right away that should tell me that I'm dealing with either a lens or a mirror. Which one do you think? The reason it is because if it's inverted, it has to be real or virtual. If it's an inverted image, is that a real or virtual image? Real, right, because the magnification is negative, which means that Q is positive. So if it's inverted, that's a real image. And here, I have an inverted image that's real on the same side as the object. That means this is my real space on the same side as the object. So is this a lens or a mirror? It's a mirror, because my real space is on the same side as the object. And then, what kind of mirror is it? Not a lens. Oh. Is it a convex or concave mirror? Concave. So my concave mirror, I would be, gosh, would I be inside or outside the focal point for this? I would be outside the focal point. So my object is here, and my image is here. So knowing those diagrams will help you. They'll help you on the problems too, like this one here. Let's see if we can just reason it out. A mirror produces an upright image. Okay, right away I don't know if that's convex or concave or flat, because they all produce upright images. The object is 8 centimeters high. The image is 4 centimeters high. So now I know what kind of mirror it is. What kind of mirror is that? Why is it convex? The image is smaller. The image is smaller. Does the image appear closer or farther away? If you have a smaller image in a mirror, like if I'm looking at myself in the mirror, I appear the same distance as I really am, because I'm the same size. But if I'm looking in a convex mirror and I look smaller, do I think that I'm closer or farther away than I really am? Farther away, because I look small, right? If I look small, if y'all were way across the quad, you'd look itty-bitty to me. And so I appear farther away. That was a question in the OpenSex. That's why I'm stressing it. Y'all remember that question? Okay. So if I look smaller, as I do in a convex mirror, I appear to be farther away than I really am. So anyway, I know this is a convex mirror. And it tells me that the center of curvature is 16 centimeters. So I know that my focal length is -8, because convex mirrors have negative focal points. I want to know where the image is located. I know that the image has to be located to the right or left of the mirror. So far I have this mirror, it's convex. My object is right here. Where is my image? To the left or right of that mirror? It's going to be to the right, because it's a virtual image, and virtual images are in the virtual space of the mirror, which is behind the mirror. That's my image, this is my object. So I can get rid of some things. I can get rid of this. It could be at the mirror's focal point. We're not really sure. Let's see. So the image is 4 centimeters high. Where is the image located? I don't really know. That's all I can really get rid of right now. So I know my focal length is -8. I know that P is equal to 8, because it's given right here. Oh wait, no, I'm sorry, that's not it. I know that the magnification is HI over HO. HI is 4. HO is 8. So I know that my magnification is +1/2. I know it's positive because it's an upright image. It says that right here. So it has a positive magnification. Now, I know that the oh, this requires you to substitute into the equation. Let's not do this one. Let's stop right there, okay? Because it requires you to say 1/2 is equal to Q over P, negative Q over P, and do 1 over F, which is -8, equals 1 over Q plus 1 over P. And I have 2 equations with 2 unknowns. We're not going to do that. I guess that's the second time we've seen that, right? Because we saw that in class, too. But anyway, it's still a good exercise to sort of go through this and think about what the mirror is. Let's look for another one, and then we'll look at some other stuff. All right, so what about this one, number 10? Use a converging lens that has a focal length of 10 centimeters. The lens forms a virtual image 20 centimeters away. What is the magnitude of the magnification? Right away, we can get rid of some answers. What answer can we get rid of right away for number 10? we know it's not A, right? It can't be A because that means that it would appear smaller. Why would you use a magnifying glass to make it smaller? I know that I'm using a converging or a convex lens. My object would be here. That's my object. And so my image is going to be over there. It'll look bigger. I know that my object has to be inside my focal point. My focal length is 10. My image distance is 20. Oh, and I drew this incorrectly, actually, because my image is not there, but my image is actually over here. And so it's a virtual image. It's going to be equal to -20 because it's a virtual image. It says this right here. Another key, I could say not that it's a virtual image, but it's an upright image. And upright images are always virtual. I want to know the magnitude of the magnification. It's going to be -q over p, but I don't know p, so I have to find p. 1 over f minus 1 over q to the -1. That's 1 over 10 minus 1 over -20 to the -1. That's equal to 20. And so the magnification is equal to minus q. No, that's not right. No, I did this wrong. This isn't 20, it's 2 over 20 is 20 divided by 3. So that's p, and then this is going to be minus 20 over 20 over 3, and that's equal to 3. I think we might have done that one. Okay? Yes, it does. If it was 150. Okay. What else do you want to look at? You want to look at some diffraction things? Okay. Are any other OpenStax stuff that you want to look at? Are there any questions standing out to you in OpenStax? Okay. I find that people have difficulty with the diffraction on knowing the different phase shifts and knowing how it relates to single slit and double slit diffraction. So let me just recap this. If I have two waves that are in phase, that means the peaks line up with the peaks and the troughs line up with the troughs. We say these are in phase. Or we can say they're 0 degrees out of phase. Or we might say that they're 360 degrees out of phase, but that's not exactly the same. I'll explain. If they're a half a wavelength out of phase, they'll look like this. And what we've done is we've delayed the beginning of that second wave by a half a wavelength. So these are out of phase by a half a wavelength. Out of phase by 1/2 wavelength, or we could say by 180 degrees, or by pi radians. So out of phase by a half wavelength, 180 degrees, or pi radians. And then if they're offset by a full wavelength, this is a full wavelength going from here to here. So my new wave would look like this. So this is really out of phase by 360. And what it means is that I have offset these two waves. I have two waves traveling through space. I've offset them by a full wavelength. And I do that with the double slit, or the single slit, or the diffraction grating by making them travel extra distances. So I make this wave travel this distance, and I make this wave travel this distance, and this one travels just a little bit more. That's my path length difference. Just travels a little bit more distance. And so, for example, if I get a dark spot over here, what must be this path length difference right here? If I get a dark spot, I get destructive interference how much extra has my wave traveled? Has it traveled 0 wavelengths difference, a half wavelength difference, or 1 wavelength difference? A half. Because when I get a half wavelength offset, that's the path length difference right here. I just give this guy a little bit extra distance to travel, and then when they get to the screen, they're offset by a half wavelength. So if that's a dark fringe, it's a half wavelength difference. Students often have trouble with that, but you will see several questions about that. In fact, you see questions like that in the OpenStax that's due next week, where asking about that, and you'll see it on the test as well. We'll do some more tomorrow in class. Now, point out, we're going to see this in class, but let's go ahead and preview it. Students often don't have a whole lot of trouble just doing the mechanics of dealing with this equation. This is for the double slit, but it's very, very similar for the single slit. You'll need practice to make sure that you understand the difference between double and single slit. The double is for bright spots, the single is for dark spots. That's really the only difference, and the order numbers are different. Students often don't have a lot of difficulty with that. Make sure that you convert your units okay, that you get your units changed okay. But let's think about if things change in this, what happens to the diffraction pattern. So if you recall, in class, I had dots. I showed you with the diffraction grading the red interference pattern with the red laser and then the green interference pattern. Do you remember which one was bigger? Was the green spread out more or was it spread out less? All right, let's see. I'm gonna draw it less, and let's see if that makes sense. If that makes sense, does the green be spread out less? Which has a longer wavelength, red or green? Roy G. Biv. Red is closer to infrared. Which is it? Is red longer or shorter wavelength than green? It's longer. So this is a longer wavelength, red. And so if the wavelength goes up, what happens to theta? If the wavelength goes up, theta is going to go up too. We're using this sort of approximation that theta is approximately equal to sine theta, which is sort of true. It is true for the most part, but the proportion is still right. That even if this isn't exactly true, that if I increase this side, then this side also has to increase. The angle theta has to increase. And if I increase my angle theta, I'm increasing the separation. So you're right, Tylisha, that the red or the green was closer together because the wavelength is shorter. The red is farther apart because the wavelength is bigger. So we'll see some questions like that tomorrow where if I increase this, what happens to this? What if I have a diffraction grating, or if I have a single slit, and I move the slit closer together? I make the slit more narrow. Is that going to make the diffraction pattern spread out or shrink together? If I make D small, what happens to theta? Keeping everything else constant. If this gets smaller, I put my slits closer together, what happens to theta? It gets bigger, right? Because this is an inverse proportionality. Kind of like, what's that? Boyle's and Charles' law is an inverse. So if one goes up, the other goes down. So if this goes down, then theta goes up. If D goes down, that means theta goes up. So what's going to happen to my pattern? Is it going to shrink or is it going to spread out? If theta increases, what happens to my pattern? Shrink or spread out? It's going to spread out. Okay, so when theta goes up, that means that you get your dots are going to spread out more. Just like it did over here, right? When I made a longer wavelength, the red dots, they spread out more than the green dots. Okay? So we'll see some questions like that tomorrow. Let's go through the old test, this exam 4, and look at some questions. And you can do the two lens thing because you'll certainly see that. When are these out of phase? Right here. How many degrees? 90 degrees, right. Because they're offset by a quarter wavelength. This is a quarter wavelength. If I go this just one more step, it'd be offset by a half wavelength. And a quarter wavelength is 90 degrees. In fact, you're not going to see a 45 degree. So, here's a good path length difference one. What's the path length difference for this fringe right here, this bright fringe? First of all, is it going to be an integer number of wavelengths or a fractional number of wavelengths? Is it going to be like an even number or a half number? An even number, right? It has to be 1, 2, 3, 4 wavelengths. Which one is it? It has to be either than 2 or 3. Which is it? Let's see. So this is 0. This is 1. So this is 2. So you're right. The answer is 2 wavelengths. It's offset by 2 wavelengths. Look, here are some questions like we were talking about there. With a diffraction grating, if I have this number and I want to know the slit separation, I'll just take the inverse of it. 1 over 4,000. Just look at your dimensional analysis, lines per centimeter. So this is going to be centimeters per line, or just centimeters, the number of centimeters between a line. And then you'll need to convert it properly. I know it can't be that. It's a quarter, right? It's that first number. I don't know what that answer is, but get 2.5 times 10 to the minus 4, but that's in centimeters, so it's going to be 2.5 times 10 to the minus 6 meters, converting to meters. Move that decimal place over twice. If your unit conversions are shaky, make sure you go back and review them, because you'll need to do several unit conversions on the test. Okay? If you want to find the highest order maximum, what you do, if you ever see this language, you say, oh, boom, theta equals 90 degrees. That's just implied by that if I'm looking for the highest order maximum. And then I say d sine theta equals m lambda, and I solve for m. So m is equal to d over lambda. I think that might actually be on your equation sheet. I'm not sure. But it's just taking sine of 90 is equal to 1. And so d is 1.7 times 10 to the minus 6. And lambda is 450. But it's in nanometers, so it's times 10 to the minus 9. And I get 3.8 for that answer. And then you need to sort of think about, what am I asking here? So several missteps that you could take. You could put 4, because you would just round up 3.8. But that's not correct. You never round that order number up. You can't have an 8/10 of an order. You could put 7, but that wouldn't be correct. But I would applaud you for your reasoning, because that's what you would be saying. You'd say 1, 2, 3, 4, 5, 6, 7. Because you would be counting the total number of bright spots, but that's not what it's asking for. It's asking for the highest order number. We did that problem in class the other day, where we counted the total number of bright spots, but here I'm looking for the highest order maximum. So what is the answer then if it's not 7? It's going to be A, 3. You'll probably see a question or two like that, where you have to find either the highest order maximum, or you have to find the number of bright spots. If you're finding the number of bright spots, then we have to count both sides and the central maximum. Yeah.
So if we did a question like that, but instead of bright spots, it was dark spots, you would just do the order number plus 1/2, or like, how would you?
I wouldn't ask that, but if you were looking at dark spots, yeah, you could draw this picture. You want to know the number of dark spots? It would be 1, 2, 3, 4, 5, 6. But I would never ask that, because do you count them on the outer edges? I don't know. Do you count them over here? No, I would never ask that. Okay. Alrighty. Anything else standing out to y'all? You want to call it a day, or you have other questions? We can, or just topics that you want me to talk about.
Can you look at number 11, the two-line system?
Oh yeah, you'll certainly have a two-end system. So this page, yeah, you'll certainly have this. And it could either be where they're farther apart or where they're really close together. When they're close together, you're dealing with a virtual object. I can look at this and tell you that it's probably going to be a real object in the middle. If they look really close together, it's probably going to be a virtual object. So you can use that to sort of gauge it, to sort of prepare yourself for it. So I just treat this as two separate problems. This is P1, F1. To find Q1, I say 1 over F1 minus 1 over P1. I just solve the lens equation for Q. That's to the negative 1. That's 1 over 10 minus 1 over 20 to the negative 1. This is 2 over 20 minus 1 over 20. Find that common denominator is equal to 1 over 20, and then invert it. So that's equal to 20 centimeters. So that means that, oh, and then the magnification is negative Q divided by P. That's negative 20 divided by 20, which is negative 1. So my magnification, or my object is going to be over, my image is going to be over here. It has a magnification of negative 1, and it's 20 centimeters to the right of that lens. And then, over here, this distance is going to be 30 centimeters. I just say 50 minus this value gives me the remaining distance. So now P2, that's going to become my value for P2. It's going to equal to 30 centimeters. F2 is 15. Exactly what I did before. Find Q2 is 1 over F2 minus 1 over P2. So 1 over 15 minus 1 over 30. That's equal to 30. So Q2 is equal to 30. M2 is negative Q2 over P2. Negative 30. Oh, this is over 32. So this magnification is negative 1 as well. And then to find the total magnification, I take the product of those. So the total, which is what this is asking for, is equal to M1, M2. So it's going to be D, positive 1. Negative 1 times negative 1. So my final image, if I were to draw it, is going to be 30 centimeters to the right of lens 2. It's going to be the same size as the original object, and it's going to be upright. It'll be sort of right. That's a little far away. It's going to be sort of like right here. You'll have a question like that. Make sure you can do it. It's really not different from a one-lens system. You're just doing it twice. Every test has a question, so practice it. And then also in your workbook, in those practice problems, there's one to try out. Alrighty? That all for today? Open text is due tonight. If you have any questions, I can answer them here. Alrighty, well, make sure you see me before you go so I can get your names